Welcome to another video on my channel. Today is going to be another topic and it's going to be on Google Slides just like last video, and I really hope you like it. But if you didn't, please make sure to comment down below that I should switch back to the old format. And if you do like it, also please show your support for this format by commenting down below. If there's really no such comments or the opinion is neutral, I'm going to stick with this, and saves me a lot of time and it allows me to give a better explanation to you. If the resolution can be better, a lot of things, it saves a lot of time and convenience for me, and also I think it produces something a little more formal for you, especially if you're not doing on as good of a screen, or if you prefer something that's a bit more rehearsed and something that looks a bit more formal, and it also helps people understand, as if you were using latex or any of the other stuff, it will be super clear and easy to understand equations. So, without further ado, let's actually move on to the actual topic. The first topic we're going to talk about is the antiderivative, or the indefinite integral. Now, antiderivative is the opposite of derivative, and it's in the name. Since derivative is just derivative, and anti is the root for opposite. So, what is integration? Integration is when we're finding a function, capital F of x, whose derivative is the given function f of x. So, basically, if we have the capital F of x, differentiate that should get us our original f of x. In the notation, there's a symbol at the beginning called the integral symbol, and this symbol is notated as f of x dx, which kind of looks like a deformed s. Now, if you look, there's a plus c on there, and the reason there's a plus c is because you can integrate something, you can differentiate many functions that have one answer. An example is x squared. X squared, the derivative of that is 2x, but the derivative of x squared plus 1 is also 2x, x squared plus 3 is also 2x, x squared plus 3,855,000 is also 2x, because when you differentiate a constant, you get 0. So there are a few rules. First is the power rule, where if you're integrating x to the power of n dx, you get x to the n minus x to the n plus 1 divided by n plus 1, and then plus c, or n is not equal to negative 1. Now, because if it's equal to negative 1, minus 1 plus 1 becomes 0, and that's about it, and then using the power rule just results in something undefined. But that same x to the negative 1 dx is actually the integrating, that is actually the natural logarithm of x plus c, just not the power rule. Now, e to the power of x dx integral is e to the power of x plus c, because the integral and the differentiation of e to the x are the exact same, and cosine of x integral is sine of x integral is negative cosine of x, and if we have a constant a times f of x plus a constant b times g of x dx, you can split those two and also bring the constant outside of the integral. Integration is really finding the area under a curve like x squared and the x-axis, but there are different situations also. Problem is how to calculate the exact area of a shape that's not exactly normal, not really a square, not really a trapezoid, nothing really similar to that, but it's bounded by functions. So, approximation was to, if we divide the area into small shapes, rectangles, and use a notation called sigma notation, which basically means the sum of all of this, and then we divide the intervals, plug in values, and use different theorems, you'll get a pretty good approximation. And I'll cover that probably later in the theory of introduction to calculus or in my main calculus series. So that's about it for area problems on approximations. Definite integrals are basically the same thing as that, except it's more specific and you actually use the antiderivative. Except you have limits where you have a is the lower limit and b is the upper limit. So it's not a times b times f of x, it's a to b, the integral from a to b of f of x dx, and then you have the limit as it approaches to infinity of all the sums. So we're taking infinite sums where the rectangles have zero width. So the geometric interpretation is, of course, the area above the x-axis by the area below the x-axis, but that's basically the same thing, and the properties are pretty similar. But I'll go into this stuff more detail when I actually cover integrals in further detail. Now, this is also a very important thing to know, the fundamental theorem of calculus, or the So, this actually connects differentiation and integration. There's actually two parts to this. The first part is the derivative of an integral. If g of x is equal to the integral of a times x, ax times f of t, then times g of t, then g dash of x is equal to f of x. If we integrate f of t, we get this f of t plus t is equal to g dash x, but everything is just a dummy variable, so it doesn't matter, and then just taking the opposite of that gets you this. For FDC part 2, which is also the evaluation theorem, it's basically the same thing as the thing we just covered, which was the definite integral to figure out the area, where if you have from a to b, you have the antiderivative f of b minus the antiderivative of f of a. What they're saying is the rate of change of an accumulation function is an original function. Now, you don't really need to worry about accumulation functions, we'll cover that later, and it's a bit more complicated, so that's not very important. So, and the second part, it says provide the practical way, but that's pretty much the only way if you're not going to use limits, and even if we use limits, taking them at infinity and using different rules can sometimes get very complicated. This is one of the more elementary techniques, and now we're going to be diving into specific techniques. So, this is called U substitution. So, let's choose substitution u is equal to g of x. Then we find the differential. Notice I didn't say the derivative, because d over dx, which is the derivative with respect to x, which means we're taking it with respect to x, which means that x is the variable that we're really going to be counting as a variable, and the other stuff are just dummy constants, unless specified otherwise. So the differential is just doing du, so you're going to add dx on the end. So you substitute u and du into the integral, and you replace all the original variables with that. Then you integrate with respect to u and substitute back. Now, for definite integral, you can either integrate, substitute back for x and use the original limits, or you can change the limits to be in terms of u of a and u of b instead of f of a and f of b, and evaluate directly. An example would be x squared times x plus 3 of 1. Now, integration by parts is another one. So, integration by parts, it derives itself from the product rule of derivatives, and it can really also be called the product rule of integrals. So, first step is identifying the formula, which is u dv is equal to uv minus v du. Now we have to choose u and dv, and the goal is to make this simpler than the original integral to figure out how to make it easier. Now there's the logarithmic, which is lineate or illate, which is logarithmic, inverse trig, algebraic, trigonometric, and exponential. Now you don't really need to worry about this. All you need to know is some functions are better suited to be u, and some functions are better to be suited dv. So, sometimes we might need to do it again and again to solve the integral. And this is actually how you figure out the integral of the natural logarithm of x using integration by parts. Now, one of the last topics we're going to be talking about is trigonometric integrals. Now, this is if we have powers of sine and cosine, and there's a lot of rules, and you can read it on the slide if you want, but I'm not going to explain all of it as it can get very complicated, especially the third column, which is trigonometric substitution. which involves with a lot of right triangles, substituting back and forth between multiple different variables, and the sorts. Now the first case is of course part of the sine and cosine. The second case is part of the secant and tangent, which is really the trigonometric, really integrals. But trigonometric substitution is kind of also part of it, so I decided to include it in this slide. The second to last topic we're going to be talking about is integration by partial fractions. This is actually quite complicated, and it involves setting denominators and a law of algebra. There's different types of factors and different types of things we can factor. So this entire box, types of factors, distinct linear, repeated linear, and irreducible quadratic, all of them are basically using the same partial fractions technique, and some of the integrals are really better off like that. Now, the reason that sometimes we might use this instead of another u substitution is because the quadratics and stuff cannot be factorable, and so u substitution is very difficult and almost outright impossible. But this requires a lot of algebra, so I'm not going to go much in depth with this. But in my real calculus series, I am going to go in depth with this and show examples and everything and the source like that. The final topic we're going to be talking about today is improper integral. Now, there's two types of improper integrals. Infinite limits of integrations, where one of the limits is infinity, or discontinuous integrals. So if we evaluate the function, it basically becomes undefined, or like divided by 0 or infinity. So what we have to do is we normally have to take limits as it goes to infinity and figure out really whether it converges or diverges. And also if it converges, we can figure out what exact value it leads to. So that's about it. Thank you so much. See you in the next one, and bye-bye.